Our started recording, assuming you consent to do so.
Okay.
Okay, so we'll begin our second lecture of the morning. Professor Yuri Kovchegov from the Ohio State University will tell us about TMDs at small x. Yuri knows everything about everything that gluons can do. So we hope that's what he will tell us. Go ahead, Yuri.
Okay, all right. Well, thanks for the introduction. So I'll talk about TMDs at small x, as you have just heard. And I'd like to encourage everyone to please interrupt me and ask me. I understand this is not an optimal setup. I see a video of the room, but I don't see each of you individually very well. So
I'll let you know when there's a question.
You'll let me know? Okay. Thanks.
Also raise their hand to ask the question.
Yeah, I mean, the organizers, I mean, Chris said that, I should allocate 15 minutes at the end of my talk for questions. Ideally, I would like to have it more dynamically. I would encourage people to interrupt me and, and stop me and ask me questions during the talk rather than saving them till after the talk. But, whichever way works for you guys is fine by me.
Sounds great.
Okay, so on to the actual talk. So I'll do PowerPoint slides, as you can see, but of course, if there are in-depth questions, I have my tablet here standing by, so I can also write something on the tablet if need be. So the outline of the talk, the plan is kind of maybe twofold. My goal is to introduce you to small x physics. I understand some of you maybe are kind of budding experts in the field. Maybe some are, I've never looked at small x physics, so there's probably quite a discrepancy of backgrounds. So I'm not assuming anything about your small x background. So as part of the introduction to small x physics, I'll first talk about sort of general concepts and talk about the classical small x physics, multiple rescatterings in a dipole picture of deep elastic scattering, black disk limit, Parton saturation, saturation scale. I'll discuss the McLerran-Venugopalan Model, saturation scale for a nucleus, and how it relates to TMD. I guess the first brush up with TMDs in my talk will be in this part. We'll talk about Weizsäcker-Williams gluon TMD of a large nucleus at small x. Then we'll move on to including small x evolution corrections, and we'll discuss nonlinear small x evolution equations, their solutions, how they preserve unitarity, how they lead to energy dependence of the saturation scale, and if time allows, we'll even talk a little bit about geometric scaling. And we'll summarize it all in a sort of an oral map of this high-energy small x QCD picture. By the way, this is an outline for 2 lectures, and even for 2, it's probably a lot of stuff. But since this is a TMD school, the second half, or the second sort of part of my talk, or third one, I guess, in this classification, but maybe time-wise it will be the second lecture, we'll see how it goes, is to discuss TMDs at small x. Can all this machinery, classical, small x physics, nonlinear evolution corrections, can it tell us about TMDs at small x? And I'll argue that yes. And I'll at least give an overview of the results for some of the TMDs that we understand their small x behavior for. So there are several classes of TMDs here. One would be, so we'll talk about how we can really sort of classify different TMDs, or try to classify them by their small x behavior, whether it's iconal, sub-iconal, or sub-sub-iconal. I'll explain what that means when we get there. But iconal TMDs examples are unpolarized TMDs, or the Sieverts function also has a iconal small x asymptotics. And then there are subiconal TMDs, like for instance helicity, and sub-subiconal is transversity. So depending on how dominant they are at small x, they're either iconal, subiconal, or sub-subiconal. The more sub it is, the less dominant they are, the less the weaker is their small x asymptotics. Anyway, and then we'll conclude. So realistically for today, the plan is to do the first bullet and maybe a big chunk of the second bullet, and then tomorrow we'll finish the second bullet and hopefully finish the third bullet. But that's a plan, and if there are a lot of questions, I'm willing to slow down and maybe cover a little bit less or a lot less, but go maybe more in depth if need be. Okay, any questions already? No? Okay, looks like no questions, so let's move on. So general concepts of small x physics. Let's really start from afar. We all know how the coupling runs in QCD, right? The coupling is weak at large momenta, it's larger at small momenta. Okay, so there is asymptotic freedom, and Gross, Politzer, and Wiltshire got the Nobel Prize for it. And then the big question we can ask ourselves: collisions, right? What's the scale of the coupling, energy collisions? And I guess many of you know this answer, of course, but somebody naive or maybe outside the field, let's call him an optimist, somebody who just says, oh, high energy means large momentum scale, right? And that means the coupling is small. That's sort of maybe a very bird's eye view of the problem, and that's indeed incorrect, right? So an optimistic view would say, well, we do high energy collisions, everything will be weakly coupled, and great, nothing to worry about. Well, of course, you do the calculation, you understand that the scale of the running coupling is not given by the center of mass energy. It's often given by a typical momentum transfer in a collision. And a typical momentum transfer in a typical, mean bias or something, hadronic collision, for instance, if you do proton-proton collisions like the LHC, you say the typical momentum is closer to lambda QCD than to typical transverse momentum, a typical momentum transfer. They're closer to lambda QCD than to square root of S. And therefore the coupling is order 1, and then we shouldn't just do perturbative QCD, right? We cannot do a weak coupling expansion. Of course, in PQCD, we know better, right? We say, okay, we look at events where we produce high PT particles. If these are proton collisions, we can do deep inelastic scattering or CDS or Drell-Yan processes with large virtualities, with large Q-squared scales. And that gives us a hard scale which justifies using a small coupling. But still, that applies to certain observables, right? Some observables are perturbative, some are maybe not perturbative, right? The total cross-section, say in proton-proton collisions, wouldn't have a hard scale like this. Or if you're not looking only at high PT particles, you want to integrate overall PT, you invariably end up at low PT where things are non-perturbative, right? So, and people try to tackle these problems. Of course, these are not new questions, but let me just give you the small x or saturation physics viewpoint on this. That so saturation physics is based on a premise, or maybe on an observation which was supported by many calculations, which shows that there is a hard scale, excuse me, called the saturation scale. It's an intrinsic scale. It's a property of a wave function of a proton or a nucleus. It grows as, so it's called QS. QS squared grows, say for a large nucleus, grows as a to the 1/3, where a is the atomic number of the nucleus, the number of nucleons in the nucleus. And it grows as a power of energy. This power lambda is calculated perturbatively in the expansion, sort of phenomenologically it's close to about 1/3 as well, such that in high energy collisions we have a scale QS which could be larger than lambda QCD. It's not as big as the center of mass energy, but nonetheless it could be hard, and it can make the coupling small, and therefore allow us to do perturbative calculations. So instead of looking for a high PT tail of the distribution, we can actually do calculations at any PT, any transverse momentum, as long as we have this hard scale in the problem justifying the calculation. So let me be more precise. It's sort of a different version of the same slide. Instead of the power of energy, I put 1/x. If you're talking about, say, a wave function of a typical hadron,
Yuri,
saturation scale goes like this. Yeah, question?
Can you go back to the last slide?
Yes.
If lambda is about 1/3, what scale compensates for the dimensions there?
That's why I have the second slide where it's 1/x.
Sorry.
It really, one has to look more carefully, of course. At the leading log level, it doesn't matter. At the sub-leading logs, it becomes important. But the scale that compensates, how do you make x from s, right? You get s over q squared or something, right? S over some typical transverse momentum scale. So that's how you get really 1/x power. And it will become a little bit more apparent maybe as we go into more details about it. But it's really that as you grow, as you increase your energy or you decrease your Bjorken x of your measurements, of your calculations, the saturation scale should grow as power of 1/x. Okay. All right. Okay, so that's really the main principle, and I just wanted to lay out up front that our calculations will proceed assuming that most things are perturbative because of the saturation scale. Of course, as a result of this calculation, we'll calculate the saturation scale, we'll find the saturation scale, and actually justify this formula here. But the calculation is done really assuming that almost everything is perturbative. Okay, how do we do the calculations? And the first take is quasi-classical approximation. So the first sort of subtopic would be multiple Glauber-Mueller Rescatterings. So let's specifically talk about deep inelastic scattering process. We have obviously some lepton scattering on a proton or a nucleus, exchanging a virtual photon, and everybody in the room, of course, knows the drill. We have x and q squared. Now, suppose I want to discuss this calculation or do this calculation at small x. So how do I go about it? Well, it's first of all, of course, the standard thing is square, right? To calculate structure functions, to calculate DIS cross-section, we just square this diagram, the proton-photon scattering amplitude, right? And we have something on the right-hand side. Somehow I'm not very consistent. My proton is now on top, the virtual photon is at the bottom. Hopefully it doesn't cause too much confusion. And that's a famous handbag diagram. And that's what you want to start with in most perturbative calculations of DIS. But this is not where you want to start if you're doing small x calculations. At small x, there is another, well, there is a contribution which is shown down here. Again, I keep swapping the position of the proton and the virtual photon. So in my lower diagram here, the virtual photon is again on top and the proton is at the bottom. So the statement is that at small x, the leading high energy behavior corresponds to the photon coming in, and in some frames, if you want to work specifically, you can work in the rest frame of the proton, but you can also work in some sort of a Center of mass type of frame where both the photon is going along, say, minus light cone, the proton is going along the plus light cone. The dominant contribution to DIS at small x happens when the photon splits into a quark-antiquark pair long before it interacts with the proton, and then this quark-antiquark pair goes and interacts with the proton, and then if you're calculating the forward scattering amplitude, you have to recombine quark and antiquark back into the virtual photon. And the gray vertical blob here involves or denotes various gluon exchanges, some T-channel gluon exchanges. And that diagram would be dominant at small x because if at high energies exchanging gluons in a T-channel is energetically more advantageous than quarks. So you could argue, oh, this diagram is sort of a one-loop correction to the Handback diagram, so it comes in with an alpha S factor. That's indeed true, but because we're exchanging gluons in the T-channel in this gray blob and not having quarks in the T-channel as in the Handback diagram, we have this extra 1/x enhancement for this second type of diagram. And, if your x is fairly small, and our alpha S unfortunately doesn't get too small, right? So if x is less than, I don't know, 10 to the minus 2, which is sort of a usual threshold for small x physics, then this alpha over x is still much larger than 1, and the second type of a diagram is enhanced compared to the first one. Okay, so we are going to be doing things in this sense that deep elastic scattering for us would be a scattering of a dipole on a target rather than a Handback diagram like this. Any questions, concerns? Okay, very good. So
question, Yuri?
Oh yeah, question. Yeah, who's speaking?
Maybe I wasn't paying it. This is Chris Lee. Maybe I wasn't. Does the power counting here become obvious from a perturbative computation of diagrams in the two topologies, and that at small x, the bottom one becomes dominant?
Is it obvious? No, it's
Does
not.
it come from a perturbative calculation, or where is the power counting that shows that the bottom one is dominant come from?
Okay, so let me try to annotate, and it's always a bit risky because somehow my computer tends to freeze when I annotate over my PowerPoint. So what I mean specifically is a two gluon exchange, right? So the extra alpha S. Oh, okay, so I think I'm having issues already. Let me actually do the following. Let me stop sharing this. Okay, at least it didn't freeze, and I'll write on my iPad. Okay.
I guess it's not obvious.
Well, if I had the blackboard behind me, it would be. It's not obvious. So we're talking about a Handback diagram like this, right? Versus a diagram where we have a dipole like that, and we have a picture like this. Okay. All right. It's a little. So you have two extra vertices here. So indeed you have an alpha S, right, compared to what you have on the left. Is that clear? But what about the power of x? Well, then you have to do a calculation, and say the rule of thumb is if you have a diagram, a high energy scattering diagram, where you exchange a particle with spin j, right, then as you can check by explicit calculations, the corresponding scattering amplitude gets for regular QCD type of couplings, the scattering amplitude at high energies scales as center of mass energy to the power of the spin j. So if you exchange if you're interested in a cross section, total cross section, which would be this diagram squared, right? It would scale as m squared over s squared, right? So it would go as s to the 2j minus 2. And so you can check, right? If we're exchanging a gluon, the scattering amplitude at high energies goes as s. Just a Born level calculation, you can just sit down and do it. Really, you get, if this is a big plus, big minus, you get a p plus from the matrix element on top and a p minus, or large p minus from the matrix element at the bottom of the diagram. If you want to look at some sort of a quark exchange diagram, for instance, something like this, if this is quark-antiquark scattering, then quark has spin a half, right? So your scattering amplitude would grow as s to the as a square root of s, and the corresponding so m would go as a square root of s. Corresponding cross sections, are constant in the case of a gluon exchange, and in the case of a quark exchange, the cross section would go as 1 over s, right? If j is 1/2. So if you're interested in high energy regime, right, where s is large, that means quark exchanges are suppressed compared to gluon exchanges, for instance, by 1 power of s. 1 power of s suppression is exactly what generates a power of 1 over x enhancement for the gluon exchange, right? Because s at small x, again, s is roughly q squared over x.
Okay.
Does that make sense?
Yeah, so it's actually the spin of the exchange particle that was crucial.
Yeah, ultimately it's a spin, and you can kind of connect to Reggie physics, but I don't think I have time to go that deep and that back in time. But if you don't know anything about the spin, you can just, the students in the room can just sit down and calculate those scattering amplitudes and take the high energy limit and convince themselves that this counting is indeed correct. And ultimately, right, people know that at the LHC, right, at small x, even for Higgs production, it's really gluon PDFs which dominate. Well, maybe not for Higgs, but at least for other hadron production. It's a gluon for hadron production in PP collisions. It's a gluon PDFs which dominates. So it's kind of maybe part of that folklore, but ultimately this feature is based in this statement that gluon exchange is dominant over quark exchanges at high energies.
Okay, thanks a lot.
Okay, all right. Let's get back to the presentation. All right. So if we now buy this, let me go full screen. If we buy the statement that this dipole picture dominates, so this is how we do the calculation then. We have a separation of time scales, right? The virtual photon comes in and splits into a quark-antiquark pair way before the interaction with the proton. So we have this splitting process, and conversely the merging process on the other side, which we can factor out. These usually factor out in the form of the wave functions, this light cone wave function squared. So we have on the left of this process, we have a light cone wave function for the splitting of a virtual photon into quark-antiquark pair. And it depends on, of course, it depends on the virtuality of the photon. I'm not writing that explicitly. It depends on the longitudinal momentum fraction of this virtual photon carried, say, by the quark, which we call z. So quark carries the fraction z of some q minus momentum of the photon. The antiquark carries a fraction of 1 minus z. Moreover, we have this quark-antiquark pair. They have some relative transverse momentum between them, but we prefer, for the reasons you'll more or less see in a little bit, we prefer working in a transverse coordinate space, in the position space, x perp. So instead of the transverse momentum k perp, we Fourier transform this wave function and we work in x perp, in the transverse position space. So it's sort of a mixed representation. The wave function is the size of the transverse size of this quark-antiquark dipole and their longitudinal momenta, momentum fraction z. Anyway, so we have this wave function on the left-hand side and on the right-hand side. Now, you may ask why the transverse size of the dipole doesn't change in the interaction. And that's really the important maybe point here, that at high energy, in a high energy scattering, if you have these quarks going and interacting with a target, in the iconal, the leading order in high energy iconal approximation, the transverse positions of the quark and antiquark do not change. They don't, the recoil is negligible. Of course, there is always some recoil, but it's negligibly small. So we can neglect the recoil in this leading order high energy approximation such that the transfer size of the dipole remains the same before and after the interaction. And that's really a big advantage of this mixed representation working in a transverse position space, so that this x perp is really preserved in this high energy scattering. If that's the case, we have the wave function squared because x perp is the same on both sides, and then the interactions between this dipole and the proton are described by this function n, which is called a dipole quark dipole scattering amplitude, right? So we have this dipole QQ bar pair scattering on a proton, and we also continue to work in the x perp space. We have the impact parameter b perp, right? Just the impact parameter between the dipole and the proton, and then of course this scattering amplitude may depend on the center of mass energy, and that dependence comes in through the rapidity dependence y, which is log 1 over x. And we have to convolute, of course, we have to integrate over z, over the impact parameters, and over the dipole sizes with this integration measure. The details here are not terribly important at this point. Okay, so the Lyko wave function for a virtual photon to split into quark-antiquark pair is a known object. Actually, I don't know how many of the students in the room know light cone perturbation theory or light front perturbation theory. Can I get some sense of it, maybe by a show of hands?
Applaud if you know light cone perturbation theory.
Applaud. Yeah, the picture is too small on my screen, so I cannot really. Okay, seems very quiet.
The organizer of the school does not know light cone perturbation theory.
The organizer does not know. Okay. Let me see. How many of you know time-ordered perturbation theory?
They're not allowed to be here if they don't know time-ordered perturbation theory.
Okay, so if people know time-ordered, light cone perturbation theory is just time ordering along the light cone direction, x plus or x minus. So maybe I can. Does that explain anything, or does it still sound a little?
So it's just quantizing at a different, not at equal time.
Sorry, I'm doing something wrong. Yeah, I was trying to. Sorry, let me. Yeah, you quantize at a fixed light cone time other than fixed time, right? So I'm not gonna go in the details, but right. So for instance, so if we have this scattering we're talking about, right? So this is the x plus direction. This is the proton. This is the x minus direction, and here comes the virtual photon, which splits into a quark-antiquark pair, which leaves a long time in the minus direction, as I just argued, right? And then again we get the virtual photon gamma star. So we have to describe splitting of this gamma star into quark-antiquark pair, and that splitting can be described by ordering things along the x minus axis, for instance. So light cone perturbation theory or light front perturbation theory, we order emissions in x minus. So compared with time ordered perturbation theory, we order in time t, right? So so for instance, what I was talking about is a splitting of a virtual photon into a quark-antiquark pair. The way you calculate a wave function, you have an intermediate state, the quark-antiquark pair. It looks like a final state the way I'm drawing it, but of course it's a part of a bigger diagram up here. I just took a part where the photon splits into a quark-antiquark pair. These guys are not, well, in a standard perturbation theory, the quark and antiquark would not be on mass shell, but in light cone perturbation theory, just like in a time-ordered perturbation theory, everything is on mass shell. In time-ordered perturbation theory, energy is not conserved at the vertices. In light cone perturbation theory, well, if we order them in x minus, that means that the plasma momentum is not conserved at vertices, at the vertices. Okay, so we write an energy denominator for each intermediate state. Does this make sense, or am I going too fast?
I see Miles nodding around the room.
Mild nodding around the room?
Yes.
So I'm putting people to sleep? That's good. That's exactly where I wanted them. Okay. Anyway, I think I don't want to spend, well, let's say I don't want to spend too much time on this. So you say, well, okay, maybe I'll spend a little bit of time. So you say, okay, we have a photon with momentum, I don't know, q, quark carries momentum k, anti-quark carries q minus k, right? And like I said, the plus momenta are not conserved, so the energy denominator takes the energy, say, of the incoming photon, virtual photon, which is actually q squared plus q squared over q minus, and subtracts the energies. By energies, I mean plus momenta of the quark. Let's assume that the quark is massless for simplicity, and the anti-quark. And you have some regulator, plus or minus I epsilon. So instead of propagators, you get energy denominators. The particles are on mass shell, but that means that the plus momentum is equal to, say, k perp squared over k minus, right? So there is no more plus momentum. We just have this k perp squared over k minus, and they are not conserved, right? The plus momentum of the virtual photon is not the same as the plus momentum of the quark plus the plus momentum of the antiquark. Rather, there is a difference between those quantities, and that's what goes in the energy denominator. It's similar to what people write in time-ordered perturbation theory when they write energy denominators. And of course, if you want to calculate this object completely, you have the vertex, right? You have a g, you have some u bar of k, epsilon slash lambda v of q minus k. You put the polarizations and everything, and if you do the calculation carefully, of course the photon here can be transversely polarized, can be longitudinally polarized. It's a virtual photon, so the polarization has to be adjusted accordingly. But in the end of the day, this is what one calls a light cone wave function. So the rules for the spinor matrix elements are just standard rules of perturbation theory, nothing special there. But the point is that we have this energy denominator. And this we can do, right? This is not QCD. This is quantum electrodynamics. We just have, yeah, I put G, but of course it should be E, right? Or E sub F, the electric charge of the quarks. But other than that, this is all calculable. Is it clear? Any questions?
We're good.
No questions. Is it because it's clear or because it's very confusing? The latter.
Is there an analog in equal time quantization for, I don't know, an equal time wave function, or is that nonsense?
In a time ordered?
Yes.
Yeah, so you can, I guess, you can talk about equal time wave functions. Let me just think for a second. It's a little, you know, I usually work on a light con, so it's a little bit, there's a bit of an adjustment there. But there's certainly time-ordered perturbation theory, yes. Whether one can talk about wave functions, I don't think so. Let me just think for a second. Well, maybe, right? So I guess the question is, can we take a photon and have it oops. I'm glitching here. Can we have a photon split into a quark, anti-quark, or even electron-positron pair? Is that perhaps the question? Yeah, I think so. I think so. I think one can probably talk about equal time wave functions. Yeah. No, sorry. I think that's true. So the advantage of yeah, okay. So what I'm trying to remember is, like, if you ever heard Brodsky talk about light cone perturbation theory, he would say, oh, light cone or light front is great because vacuum is trivial. I'm not sure he still subscribes to this point, but for instance, if you have nothing cannot fluctuate into particle-antiparticle pair because, say, the minus momenta are conserved, right? So if this guy carried Q minus, this is K minus, this is Q minus minus K minus, they are conserved at the vertex, and they're always positive because everything is going in a forward minus direction. So if you start with a vacuum, a positive K minus and positive negative K minus, right? That's impossible. So that's why vacuum is trivial. At least that's Brodsky's argument but in equal time, I don't think that's the case. You can have something pop out of nothing and have non-zero energies, of course, for a short period of time and then fluctuate back or something like this. But I think the wave functions exist. They're not being used very much, as far as I know, in equal time. But yeah, so in a regular time-ordered perturbation theory, certainly one can have wave functions, or I believe one can. Okay, any other questions? All right, let's get back to the talk. I think the point of this really was to make one simple point that this part, the wave function psi, is calculable. We can calculate it just using a, the lowest order simple QED diagram, right? The coupling here is alpha alpha E and M ultimately, right? So this we know, and this is not an interesting part. It's calculable. One can do it. The difficult part, of course, as always, is QCD, strong interactions. So, but all the strong interactions here are in this amplitude n, which is a dipole scattering on a target amplitude, and that's what we want to calculate. Okay, so this is what I want to do. So the first picture, which kind of includes gluon exchanges, but also has saturation effects in it. Imagine that instead of a proton target, we have a nucleus, for instance, and a large nucleus, which is made of many nucleons. So for me, nucleus is a very simple object, and I know, of course, it's not really simple in real life, but if we have a large nucleus, it's sort of like a bag of nucleons. It's just a bag where we have many nucleons in it. And if that's the case, and we have this dipole scattering on that nucleus, how can it scatter? Well, I argued that high energy scattering happens by gluon exchanges. So those kind of like mildly wiggly lines are gluons. So what you can do is you can interact by gluon exchanges with each of these many nucleons. We're looking at the forward scattering amplitude, so we have to exchange at least 2 gluons with each of these nucleons, and that would be, this is what we want to calculate as a sort of a first take on small x physics. Okay, and all these multiple rescatterings would give us the dipole amplitude n, and like I said, the wave function is a known object. We convolute the two, we get total DIS cross section, we get structure functions f2, fl. So that would be already very useful. Okay, so if you want to do a bit more of an operator discussion, one can define this dipole amplitude like this, as 1 minus a trace of 2 Wilson lines. So let me maybe show the full picture here. So again, what we want to do is we want to calculate a quark-antiquark scattering on a target. We're talking about a high energy approximation without recoil. You have a high energy quark and high energy antiquark interacting on with a background gluon field of the target. And at high energies, it is known that you can replace a quark propagator by a Wilson line. So, and the antiquark propagator would be a Hermitian conjugated Wilson line. We're talking about high energy scattering, so these Wilson lines are on the light cone. And, so I swapped plus and minus it's accidentally here, or it's probably a formula from some other place with another convention. But so plus is minus and minus is plus. Apology for this mix-up. The quark and antiquark, as I sketched on my iPad, they go along the minus light cone, and their propagators are replaced by infinite Wilson lines from minus infinity to infinity, and they couple to A plus iconal gluon field of the nucleus. Of course, this is true in gauges. Say it wouldn't be so simple in A plus equals 0 gauge, right? Because then A plus would be 0, and then you have to talk about gauge links at infinity, like a gauge link over here and a gauge link over there. But the point is, operatorially, this scattering amplitude is defined as an expectation value of this infinite light cone Wilson loop, which is from which we actually have to subtract the non-interacting term 1 to make it a scattering amplitude, not the S matrix. And we need to resum all these multiple rescatterings. Okay. So the way we do this is, so each of these diagrams with these dangling disconnected gluon lines means that we sum over all possible connections of gluons to quark and antiquark in that dipole. So this is just sort of an abbreviated notation, not to draw everything in all the gory details. You can ask if there is a resummation parameter, right? You need to do some sort of a power counting to justify your approximation. Well, yes, you can invent a resummation parameter. It's given here. Each gluon exchange brings you an alpha s. So exchanging two gluons brings us alpha s squared. And then, and I'll argue again maybe a little later, but at a fixed impact parameter, you have an order of a to the 1/3 nucleons in the nucleus. So you have an enhancement by this a to the 1/3. So alpha s is small, a is large. And so we're summing this parameter alpha s squared a to the 1/3. Assuming that a is sufficiently large for this parameter to be order 1, and it would make sense to resum all these multiple rescatterings. Okay, so what do we do? Well, one can write a simple, not a simple, but one can write an equation that as the dipole propagates, also, sorry, I guess along the minus light cone in one step of evolution, well, in one step, not in evolution, and it's traversing in this light cone direction, we can pick up an additional rescattering on a nucleon with a two gluon exchange like this, and write down an equation which really leads to simple exponentiation of its interaction with one nucleon, such that the dipole amplitude is given by this formula here. Remember, x perp was a transverse size of this quark-antiquark dipole. And there is a scale here, which we call QS, which comes up from the calculation. Indeed, right, the object in your exponent has to be dimensionless. If we have something which has dimensions of distance squared, the x perp squared, then it has to be something which has dimensions of mass squared, and that's the scale QS squared. And then there is also a log of the infrared cutoff, which comes about if you do the calculation. So this QS squared contains a lot of information about the nucleus, but we'll discuss it a little later. So this is what comes out from this calculation. We're resumming these individual rescatterings, and if we resum them all, the result is just an exponential of a single rescattering, and this 1 minus exponential again removes the term without any interaction. So that if we expand this, we at least always have one interaction with the target. Any questions so far? Am I going too fast? I mean, I know I didn't derive this, so this is just a formula pulled out of thin air. But so feel free to ask about it if it's not clear.
I don't see anyone doubting your formula.
Okay, if everybody agrees, very well. Let's just maybe to give you a physical sense, just to justify that this is a correct formula, let's just plot it. It's not my formula, by the way. L. Miller derived it back in late 80s or early 90s. So this is this amplitude n as a function of the dipole size x perp, right? And suppose we want to plot it as a function of x perp. You see, indeed, when x perp goes to 0, this 1 and the exponential cancel each other, so the amplitude goes to 0. Now, what does it mean? Well, it means that if you have a quark and antiquark, and the distance between them is very, very small, right? And this quark and antiquark, remember, they came from a virtual photon, which carries no color, right? So the quark and antiquark have equal and opposite color charges. And if the dipole is very small, they pretty much cancel each other, right? So the interaction should be weak. If you have a small object made of quark and antiquark with canceling equal and opposite color charges, it's like having no object at all, right? It's like having no dipole there. So when x perp goes to 0, the interaction goes to 0. And this is good, right? This is, oops. Okay, sorry, I clicked on something, and hold on, I'll be back. Something there which I shouldn't have clicked on, but I'll find my way. Yeah, okay. So this property is called color transparency, right? When we have a very small probe going through a target, it just barely interacts with the target, or ultimately when the size is 0, it doesn't interact with the target. Now, if we go in opposite direction, if we increase the size of the dipole, the interaction gets stronger and stronger, and that's why naturally you see this curve grows as x perp squared. And if we don't have multiple rescatterings, right? If we just keep this to the lowest order, to the single rescattering, so in other words, take this 1 minus exponential formula and expand it to the lowest order and plot it as a function of x perp squared, it will just grow unchecked as pretty much a parabola times a log, right? As a function of x perp. Now, is that good or bad, or what's wrong with this? Well, what's wrong with this is that there is this black disk limit. So if you and this is known from very general quantum mechanical principles, that if you scatter on a disk on a black disk of radius r, your cross section in principle cannot be larger than 4 pi r squared, and at high energies it's actually even more restricted to 2 pi r squared. It's not just pi r squared, it's not just the cross-sectional area of the disk, but it's 2 pi r squared. And the reason for that is quantum mechanical. You have to look at the S matrix and see how small it can get for high energy scattering. Anyway, the total cross-section for the dipole interacting on a nucleus is in the upper right corner here. It's the integral of this amplitude n over all input parameters b times 2. So the black disk limit 2 pi r squared corresponds to n equals 1, because then the integral d2b gives you pi r squared, and with a factor of 2 out in front you get 2 pi r squared. So the dashed line here is the black disk limit. You cannot exceed that black disk limit in high energy scattering, and a single rescattering here nonetheless would have generated a violation of the black disk limit. But the point is that when the dipole gets large, the interaction with nucleons gets stronger, and it doesn't interact just with one nucleon, it interacts with many different nucleons, right? And that's why we have all these multiple rescatterings resummed, such that in the end of the day, you see that when x perp gets very large, because of this 1 minus exponential formula, the full curve, the entire curve, never really exceeds 1, right? When x perp gets very, very large, the exponential just dies off, and n approaches 1 from below. So you do not exceed the black disk limit because of multiple rescatterings. So this is kind of the first example of saturation. You have something which naively, in a sort of a single interaction case, would have violated the black disk limit, but because you have all these multiple rescatterings, you never really violate the black disk limit, and the interaction always stays below 1. The scattering amplitude, sorry, stays below 1. Moreover, the saturation scale here, well, if you do a full calculation, which I'm not going to, but you can show, and I'll argue a little later, maybe on the more physical grounds, why, but in this picture, saturation scale scales as a to the 1/3. So it increases with the size of the nucleus. And you see the transition between this growth regime and the regime of kind of approaching the black disk limit. The transition between those two regimes happens about around this 1 over qs for the dipole sizes of the order of 1 over qs. And if qs is large enough, these distances 1 over qs can be perturbatively short, right? So if you have a large enough nucleus, if you just scattering on a very large target, so if A is large, qs squared can be large, 1 over qs would be small, and you may have therefore weakly coupled dynamics, right, while you still are transitioning from this growth regime to the approach to the black disk limit regime. So this is an argument that this transition to saturation, at least for large enough a nucleus, could happen in a weak coupling regime and could be understood by perturbative methods, by doing small coupling calculations. So this is part of what I was advertising in the beginning, that large nucleus may mean small coupling and therefore perturbative description of the transition to the black disk limit. Okay, so far so good. Any questions about this picture or anything related to it?
I have one question.
Yes.
Instead of the x curve doesn't change at all because it's iconal, but because it's higher speed or whatever. So the distance, we're really just looking at like the distance over 2 as x curve for this entire thing. So if there's no difference in the distance, then nothing happens. And at a certain point it saturates, but the x perp stays constant throughout the entire thing, correct?
Correct.
And it's just a measure of the distance between those two quarks, the quark and antiquark.
Right. So let me switch to my iPad to doodle if I heard the question correctly, but I believe I did. So yeah. So right. So what happens is the size is not right. The transfer size of the dipole in this high energy scattering is x perp, and it doesn't. So through all these multiple rescatterings, it does not change, right? So we have all these multiple rescatterings, x perp remains the same. But why am I plotting the answer as a function of x perp? Because ultimately, of course, you can vary x perp, you can change x perp, right? So remember, I said we have this virtual photon, right? It has virtuality q squared with these fractions z1 minus z. So these light cone wave functions, which I didn't finish the calculation, maybe I just sketched the calculation for, the light cone wave functions make sure that your typical x perp, typical for a scattering with a given q squared, typical x perp is, let's say x perp squared is 1 over z1 minus z q squared. And if you're really careful, you also include the quark mass squared. So if you want to vary x perp, you have to vary q squared first and foremost, and then of course vary z. So experimentally, varying x perp is not that easy, right? Because you integrate over x perp, and you get some, this wave function generates some sort of Bessel functions like k1 of something like x perp times the square root of everything I just wrote, z1 minus zq squared plus mf squared. You have to square this thing. There are various prefactors. You have the amplitude n, and you integrate over d2x perp and dz and d2b. So x perp, of course, is an intrinsic variable of the integral if you're interested in DIS cross-section. But you can argue, because of these Bessel functions, that the typical x perp is kind of inversely proportional to 1 over q. If q is large and z is not extremely small or extremely close to 1, people argue that it's some sort of a number over q squared. So loosely speaking, you can think of x perp as being just 1 over q. And there are caveats to the statement, but this is sort of to better understand that it's just 1 over q. So if you want to experimentally vary x perp, you just vary q, so DIS with large q squared corresponds to smaller dipole sizes, DIS with lower q squared corresponds to larger dipole sizes. Did I answer your question, or did I mishear it?
Yes.
Yes? Is that a yes?
Yes, thank you.
Okay, thanks. Okay, let me see if I can go back to the PowerPoint. Any other questions, by the way?
There's one more question in the room.
I have, I guess, a separate question. This is your function.
Very hard to hear, sorry.
So in your function, if you substitute x perp equals to 1 over lambda, in the exponent you get 0, right?
Yeah, right. This is not an exact statement. This formula is true for x perp much smaller than 1 over lambda. So yeah, I don't think I let me switch back. All right, so let me switch back to the tablet again. Sorry, it takes a couple of seconds. All right, so n of x perp and whatever else, let's say of x perp is just 1 minus e to the minus 1/4 x perp squared qs squared log 1 over x perp lambda. The question was this: if x perp is 1 over lambda, the log vanishes, the exponential becomes 1, the amplitude goes to 0 again. Yeah, as written mathematically, it's a correct statement. However, this formula is valid for x perp much smaller than 1 over lambda. I think, yeah, if you want to extend it to x perp just less than or equal to 1 over lambda, the formula becomes something like this. So when the log vanishes, you still have a 1, which doesn't let your amplitude become 0. So the 1 people usually neglect in all the talks, but when you actually do the calculation, you have to include it. Yeah. Did that answer the question?
Yes.
Okay. Any other questions, anyone? Okay, if not, let's go back to the slides and try to maybe discuss it at a slightly different way, something known as the McLerran-Venugopalan model. And again, let's start a little bit from afar. This is something I'm sure many of you, most of you have seen. These are just PDFs for a fixed q-squared plotted as functions of x. Valence up and down. Sorry, it's x times PDFs, not just PDFs. You have valence up and down quark ones. You have the C quarks, and then you have the gluons. And as clear from this plot, at small x, C quarks and gluons, their numbers are much larger. Of course, they dominate over valence quarks, and moreover, gluons also dominate over quarks at small x. Okay, so the MV model kind of says the following: if you have all these many particles crammed into the proton, right? If you go back to this slide, you say, oh, we have, you know, a fair number of gluons, quite a large number of gluons in the proton. How do we picture it, right? The proton, yeah, there is something called diffusion, but let's forget about it. Roughly, the proton radius remains on order of Fermi. You want to cram all these particles in there. You realize that if you look in the transverse plane, the proton will be a pretty dense system of many gluons. So what people draw is a picture like this, where each colored little blob is one of the new gluons or C quarks. And the argument due to Larry McLaren, Roger Venugopalan was, you have this large occupation number, large number of quarks and gluons, especially gluons, in a proton or nuclear wave function. Large occupation number leads to the classical field. So the field of the gluon field, let's say, of this system should be a classical field. Well, so how do you kind of justify it in other ways? Is you can imagine a nucleus like this shape on the left. Remember, I said for me, a nucleus is just a bag containing many nucleons, and nucleons are kind of all those little balls in that sphere. You boost it, and then you have, for a probe, that's say, so you have, of course, Lorentz contraction, and then if you send a probe interacting with this system, you see that at a given impact parameter, the probe is likely to interact with several different nucleons because they're kind of sitting on top of each other for that probe coming in from the right. And then you can do, you know, a very basic undergraduate level nuclear physics to argue that the radius of the nucleus scales as a to the 1/3, where a is the number of nucleons, just because the density of nucleons in the nucleus is roughly constant. with atomic number. So that means that if you look at, say, how many gluons you have in the nucleus per unit transverse area, you have 8 to the 1/3 times more gluons than you had in a single nucleon, just because you have an order of 8 to the 1/3 nucleons at each impact parameter. So you get this kind of like a very simple enhancement of the source strength by just having many nucleons kind of aggregate and produce this general strong gluon field. And that's really the origin of this QS being large. If QS is large, the coupling is weak, and if you take a weakly coupled field theory, you know that it's dominated by the saddle point of your action, therefore the leading gluon field is classical, and that was the original argument of the MV model. If you want to calculate the gluon field of a nucleus, you have to take the classical gluon field. Okay, this is sort of stating the same thing, maybe in a bit more detail. I think I'm going to skip it in the interest of time. This is another sort of take on it. Maybe I should spend a little bit of time discussing this. So suppose you have a probe going through a nucleus. This probe is this horizontal line. A nucleus is this circle here, and nucleons are those little circles inside. And the probe interacts with each individual nucleon separately and gets some transverse momentum KT kick. And imagine, you know, the nucleons are completely uncorrelated with each other. So it's pretty much like a random motion in momentum space. It just receives random transverse momentum kicks from the interactions with each of the nucleons. If it's a random walk, we get the overall transverse momentum broadening. Scaling is the square root of the number of kicks. Number of kicks is proportional to the number of nucleons at a given impact parameter, which is 8 to the 1/3. So delta K scales the square root of 8 to the 1/3. So the transverse momentum square scales as the accumulated transverse momentum after many kicks scales as 8 to the 1/3, and that is the same thing as the saturation scale. So saturation scale is also very intimately related to this transverse momentum broadening and scales in the same way. Anyway, so the MV model states that if I want to calculate a gluon field, A mu, of a nucleus, we just solve classical Yang-Mills equations, and that's doable. I'm not going to bother you with details, but one can solve classical Yang-Mills equations for a single source, nucleus, or proton even, analytically. And one can find the gluon field. And then what do you do with this gluon field? Well, you can calculate the gluon TMD, right? This is a TMD winter school, so you can take the gluon field and calculate the unpolarized gluon TMD at small x. And that indeed is also doable. So, okay, this is just a diagram what this gluon field looks like. Classical fields, as some of you may know, correspond to tree-level diagrams, and so that's a tree-level diagram. And we can discuss it more. So there are no loops, even though it appears there are some loops. They're not really true loops here. So this is a classical field. It's not a trivial field. It's a complicated field. It's in some sense all orders in the coupling, and it again resums the powers of the same parameter alpha s squared 8 to the 1/3 as the multiple rescatterings we discussed earlier. So if you know the field, how do you calculate the TMD? Well, that's pretty straightforward, right? You start with a definition of a TMD. And I presume there was plenty of lectures here and everyone has seen definitions more sophisticated than this one, but really I'm just taking unpolarized gluon TMD, F plus I correlator with some Wilson line staple. And suppose I'm looking at the CDIS type of Wilson line staple, so it's a forward pointing Wilson line staple. If you choose to work in A plus equals 0 light cone gauge, then one can actually choose a sub gauge of that gauge to eliminate the Wilson line staple. So U becomes trivial. And also in A plus equals 0 gauge, your field strength tensor F plus I becomes very simple. It's just a derivative of the field AI, right? A plus field is 0 by your gauge choice. So when dust settles, your TMD becomes just a correlation function of two transverse gluon fields. And like I said, if you know exactly what the classical gluon field is, then you can calculate this classical gluon field contribution to this TMD and argue that at small x, at least in some regime, that might be a dominant contribution. Okay, so people did that many years ago, obtaining, well, in the small x language back in the 90s, the standard name for this quantity was the unintegrated gluon distribution, which nowadays corresponds to this Weizsäcker-Williams gluon TMD. The exact relation between Fg from the previous slide and phi, the unintegrated gluon distribution, is here. They're kind of off by a factor of x and pi. I hope I didn't screw up any other factors in the relation, but that's roughly how they're related to each other. And we just need a correlation function of two of those gluon fields. So when the dust settles, you do this calculation, you end up with this unintegrated gluon distribution, which actually looks in some way similar to the dipole formula we just looked at, this 1 minus exponential. It's divided also by this, what used to be size squared of the dipole, and then you do a two-dimensional Fourier transform. Underlines are two-dimensional transverse vectors. So it's a Fourier transform like this. And again, you see this saturation scale arising as well. Okay, you say, so what? What's the big deal? Well, let's just look at the properties of this unintegrated gluon distribution, or just unpolarized TMD. First of all, it's sort of a calculation from scratch, right? I haven't done any evolution. It's really a calculation in a model, rather, right? In this MV model, but it's a model that does have. It's not completely ad hoc, right? For a large nucleus, it's probably the dominant contribution to the TMDs at small x, at least in a certain regime before small x evolution becomes important. So one can plot this distribution phi as a function of kt, as a function of transverse momentum. And what does one see? Well, one sees that at large kt, you have a fall of qs squared over kt squared. Yeah, I have some formulas here. I don't know if you guys want to follow, but really the logic is like if kt is large, right, that means xperp should be small. If xperp is small, we expand this 1 minus exponential, we get a log. We Fourier transform the log. Two-dimensional Fourier transform of a log is just 1 over kt squared. So we just get a usual perturbative 1 over kt squared fall off of this distribution, as you have for most TMDs, at least leading to its TMDs at large kt. But in the infrared regime, right, in the low kt, low means below qs, still above, of course, lambda qcd, where all this calculation, perturbative calculation would break down. So at low kt, xperp is large. If xperp is large, we drop the exponential with Fourier transforming 1 over xperp squared, and the Fourier transform of that is a log. Two-dimensional Fourier transform is a log. So instead of being 1 over kt squared divergent in the infrared, this this TMD is actually divergent only logarithmically at low kt. Right? So if I want to say integrate over all kt, what saturation scale does, it screens the infrared, right? The singularity before, at the lowest order, was just 1 over kt squared, which, of course, if I try integrating it over all kts, I would have a logarithmic divergence in the infrared. But because of the saturation effects, the divergence softened to just a logarithmic divergence, which is integrable over kt. Right? So the divergence is pretty much regularized. I mean, there's still a divergence, but it's integrable now. And I can calculate the total number of gluons here while still being in a perturbative regime, right? Still having the qs justifying the small coupling constant. So this is the point. Another way to understand this plot is to multiply it by kt, right? So kt is sort of like a phase space factor, a two-dimensional phase space factor. So I can take this plot and multiply it by kt. By the way, all these plots are just sketches by hand. So I don't vouch for the literal accuracy, but I'm just trying to illustrate the trends here. So KT times the gluon TMD here looks like this, right? We had 1 over KT squared fall off. Now it's 1 over KT. In the infrared, we had the log divergence. Now it's KT times the log, so it goes to 0. And there is a maximum somewhere in between around the scale QS. So this picture is even better because it shows that in this classical gluon distribution, in this classical gluon wave function, most gluons are sitting around the transverse momentum close to QS. And again, if QS is large enough, because it scales QS squared scales as a to the 1/3, if QS is large enough, most gluons are sitting in the perturbative region with KT of the order of QS, and that justifies our application of perturbation theory, right, of using the small coupling in this picture. Okay, so that's another way of understanding saturation, just by looking at the wave function of a single nucleus and calculating the classical, calculating the classical field and calculating the classical gluon TMD. Okay, so summary so far, we have applied this quasi-classical small x approach to DIS. In a dipole picture, we obtained this Glauber-Mueller multiple rescattering formula for a dipole and a nucleus. We saw that the onset of saturation ensures the black disk limit is not violated, and hence the unitarity is not violated. And in a way, we can actually argue that saturation is a consequence of unitarity. We also discussed the McLerran-Venugopalan model for the small x wave function of a large nucleus. And we saw that in both cases, the onset of saturation means that there is appearance of at least potentially a large transverse momentum scale, the saturation scale. So at this point, I want to pause and see if there are any more questions, please. I can even go back to the maybe slides with some plots.
There's a question here.
I'm probably just connecting dots that aren't here. Can you go back to the kind of the definition of phi a, the functional form of it in terms of that exponential?
Sorry, I didn't quite catch the beginning.
Yeah, right there. If you're the gluon classically, I look at that and I see something that looks something like a partition function. Is there any way that you can describe these transverse momentum distributions using StatMech if you're treating the gluon classically? Connecting dots that aren't there.
Yeah. Not the gluon. So the gluon calculation was as I kind of described. There was at least, let me just think out loud. Naively, I don't see a connection to some sort of statistical systems, right? We are talking about we just take the definition of TMD, simplify it in A plus equals 0 gauge, and then take the classical field A perp in that gauge, right, and just construct a correlation function. So my only recollection about connection to statistical physics is maybe as follows. You do have some sort of a fall-off. So by the way, and these plots are functions of KT, so these are two-dimensional distributions, right? If you really have a statistical system, you will have some sort of a I don't know, Bose-Einstein distribution in 3-vector of momentum, right? It should be isotropic, but of course we're talking about high energy collisions. We certainly broke this rotational symmetry, right? The isotropy symmetry, and we're living in two-dimensional transverse space here. So something I didn't mention, but maybe I should. So this distribution function goes as 1 over alpha s. Alpha s is the coupling, and that corresponds to the gluon field being order of 1 over g. That's just a classical gluon field. You would expect that as well. One can, and I'll mention it hopefully tomorrow, one can ask the same question: can you calculate a corresponding quark distribution function? Well, how do you generate a quark? You just put in a quark loop here at the very end, and that introduces an additional suppression by alpha s quarks, right? You need to have a gluon split into a quark antiquark pair that brings in an alpha s suppression. So this 1 over alpha s vanishes for the quarks. And then at some point, and that was an order of 20 years ago, so don't ask me for details. I remember there was a paper by L. Miller arguing that there is some connection to Pauli exclusion principle for and this the analog of this distribution, but for the quarks, right? If you have a Fermi-Dirac distribution, right, it's always less than 1, so you have something that starts out as a constant, and then maybe at larger energies, for instance, it falls off. So one can kind of, for the quarks, one can probably stretch this a little bit and do some analog with a Fermi-Dirac distribution and Pauli exclusion principle, but I don't remember the details, and I don't think it has received much development since then. So yeah, that's the only thing I can say. Of course, you know, for any statistical system, you have exponential fall-offs at high energy, right? And this fall-off is power law, because this is diagrammatic calculations, right? This is a perturbative picture. So I think any analogy you can construct is kind of a bit more qualitative than directly quantitative.
Okay, thank you.
Okay. Any other questions?
I have one. Can you hear me?
Yeah.
Okay. Just one very simple question. You have this distribution when you flatten in the boosted frame, you assume sort of an average density of nucleons, but it seems like, you know, there would be some, you know, denser thing toward the center. Do you think there's anything sort of lost by not looking at that more carefully?
Oh, no. It's done a lot more carefully than I'm letting on.
Okay.
You know, after all, this is a school and I only have 2 lectures. I don't have the time to give you all the gory detail. What I'm shoving under the rug, well, one of the many things maybe. Let me go back to the iPad. Right. So the question was, what about the fact that the density of sources varies at different impact parameters, for instance, right? And what about fluctuations? Maybe I'm not sure if that was part of the question. So the way you construct it really is actually more subtle. First the ballpark answer, that this object phi of xkt squared is whatever it was, some Fourier transform of this type, and then there is this 1 minus e to the minus 1/4 x perp squared qs squared. Now qs squared really depends on the impact parameter b as well, and there is this log that people were asking about. So in full generality, there should also be an integral over all impact parameters, right? B perp is a position. So in a standard TMD literature, what I call x perp is called B perp, right? So B perp is a conjugate for k perp in a standard TMD literature. In the small x literature, we have distance x perp, and then there is a true B perp, which is a position, right? So we could consider a position somewhere inside the nucleus or inside the proton, say, in relation to the center of the nucleus. And that is B perp, that is the impact parameter. So certainly the fact that, say, nucleus has a profile in B perp, that comes into the fact that saturation scale really depends on B perp. So this is the nuclear or nucleon profile. Okay. And then, of course, if you are, so I hope it answers at least part of the question.
Thank you. Yes.
Okay. To go maybe a little bit further, I'm not going to go into all the gory details here, but how do you solve for the classical Young-Mills field, right? You say, okay, I write my classical Yang-Mills equations, but then the question is, what is the source current? And what you do is, well, loosely speaking, you say the source is just a whole bunch of quarks or larger X gluons in the nucleus. The most basic picture, imagine each nucleon is made of 3 valence quarks, and then the nucleus is just made out of those nucleons with 3 quarks each, right? So it's just already like a Jackson E&M type of problem, except that it's not E&M, it's Yang-Mills. But you have those point quarks kind of going ultra-relativistically, right? So they're all flying to the right somewhere. Their color charges are kind of random, except that each 3 of them have to be color neutral because they form a single nucleon, right? So you have some sort of color constraints, and then you can, and then of course, so they produce the source current, but that current would have to know of the transverse positions of all those many quarks, right? So you have many different quarks in different nucleons in your nucleus, and they all have transverse positions. They also have different X- locations. So you really have to do it so there are 2 ways of doing it. You either track them all, and in the end of the day, when you're calculating your expectation value in the state, you have to kind of average over all such positions, do the color traces and everything. Or sometimes people just say you have the plus current component, which is dominant, which is proportional, well, it's a delta function or almost delta function of X minus, and then you have something called the color charge density rho, which varies with the transverse position in the nucleus. So instead of having a discrete, bunch of valence quarks, you just write some continuous function rho, but then when you calculate your TMD, again, you have to average over rho. So you need to average over rho of X. So in other words, you solve your Yang-Mills equations, you get your transverse field A sub I, which is a function of position, but it also knows about the source distribution, rho, and then you do this AI correlator, and you have to kind of integrate over all rho, and apparently what works for the MV model in a sense is what's justified for a large nucleus and equivalent to kind of tracking the positions of all those point quarks is to have some sort of a Gaussian distribution in rho with some width mu squared, which is related to QS squared. And there's a color trace here as well. Okay, so in the end of the day, yes, all those things have to be included, right? I am shoving a lot of details under the rug just because of limited time and the volume I want to cover of the material. But yes, you treat the sources very carefully, either as discrete bunches of charges inside each tiny sphere, which is a nucleon, or you can write down some sort of a continuous color charge density rho, and then you have to average over it when you're calculating your correlators, when you're calculating your TMDs, or when you're calculating physical observables like cross sections as well. Okay. Does that make sense? Or
yeah, thank you. One last tiny question maybe is when you draw those individual quarks now for each of those nucleons, the positions I assume are frozen just like everything else was, right? The particular
in a scattering process, the positions are frozen. Of course, when you're averaging over many events, when you're calculating the expectation value in a proton or nucleus state, you have to integrate over all those positions.
I have a question: is the color distribution also frozen for that event, for that?
Well, so color is like that. So say let's just take a simple. So color is a little tricky. You cannot really freeze color because then you're not going to emit anything, right? So suppose you have a just a single quark. Forget about the nucleus and all these complications, right? Suppose you just have a point ultra-relativistic quark moving along the light cone, and you're asking yourself, what is the gluon field produced by that quark? And forget about Yang-Mills even, right? Just linearize your Yang-Mills, assume that the coupling is weak, so the leading order gluon field is this thing. Oh, by the way, I forgot to ask, is that familiar to the audience that you can write a field as a Feynman diagram, and that you can write it as a Feynman diagram where this wiggly line is off shell. I don't see any reaction. I thought I saw some positive nodes, but yes, no? Okay, let me explain what I'm saying. It sounds like a no. So let's forget about QCD. Let's just do QED. Right, in QED you have Maxwell equations and say Lorentz gauge, box A mu equal to J mu. Chris, by the way, am I out of time?
Yes, but you should explain this.
Okay, I'll explain this and we'll stop here then. So these are good old Maxwell equations. Boxes are good old friend Lambertian operator, right? You can solve it. 1 over box J mu. Right? Of course, you ask, oh, what's 1 over box? Well, you know what it is, right? It's a green function, so a mu of x is an integral, say, d for y. You have some, well, in principle, d mu nu of x minus y, j nu of y, right? Where this is a green function. It's a Fourier transform of 1 over box. Well, it is, sorry, 1 over box. It's a 1 over box in the Fourier sense, right? You write it, too many two-dimensional integrals. D for k over 2 pi to the 4th e to the minus I k dot x minus y, and you get k squared here, right? That's what 1 over box is. Okay, up to a sign, we can argue about, i's and such. You look at this thing and you realize, oh, I know what this is, right? I've seen it somewhere. It's really a Feynman propagator if I put plus I epsilon. You can actually argue that because these are classical equations you're solving, it shouldn't be a Feynman just I epsilon, it should be more like a retarded green function, right? So this is a retarded green function. So it's not just plus I epsilon, it's plus I epsilon times the zeros component of the momentum. I hope people have seen this before, right? Okay, I see some nodes now. But nonetheless, let's assume for simplicity that this is a Feynman propagator. Then what is this formula that I'm putting in a bubble is? Well, diagrammatically we have the source, which is, say, maybe our point quark, or since it's QED, it could be an electron. And then we have a gluon line, which is a propagator, mu nu. And up here is the point x, where we measure the field, a mu of x is measured here. Here is a point y, which is being integrated over in the integral. So the gluon field, at least Maxwell equations, is just this lowest order Feynman diagram. This is, again, this line, the fourth, sorry, I keep saying gluon when I declared that I'm talking about QED, but I hope it doesn't cause any confusion. In QED, of course, the wiggly line is a photon. If it was QCD, it would be the gluon. This line still brings a propagator, right? This is a propagator d mu nu. So classical fields correspond to Feynman diagrams. In QED, in a linear theory, that's all there is to it. You have sources, and then you just hit a source with the green function, and you get a mu. I mean, one can be a bit cavalier and say that I just explained pretty much all of Jackson. That's true at a very conceptual level, of course, not in all the many details. So similarly, one can talk about QCD. So in QCD, let's say, we have the same picture, we have a quark, we have a gluon field. The only difference, though, is that the gluon field has a color, A, right? And the vertex here has some TA with colors, say Ji, where outgoing quark has color J, incoming quark has color I. So this is a lowest order field. The field I showed you in my slides is a more complicated field that's resum all orders in the coupling times this a to the 1/3 enhancement. So it includes some resummation. But the question was whether the color is frozen. Well, I think this diagram shows that the color cannot be frozen. The color is frozen when the quark is, say, flying without emitting anything, right? The color is the same frozen at I being 1, 2, or 3, right? So these are color indices I and J. But the second the quark emits a gluon, the color is bound to flip to J, right? The color rotates. So the color is not frozen. The color is sort of treated like it's treated in any Feynman diagram. It's frozen without interaction, but once you have interactions, the color flips. So that leads to a subtlety that the current, the source current J mu, right? It also has a color index mu, and in a way, the color index A, in a way, is proportional to this Ji element, Ji element of the TA color matrix. So the source current somehow knows about. It's more like a matrix element. It's like a transition element in color space. It knows about the initial and final states, colors of the quark in the initial and final state before and after emitting the gluon field. I don't know if that helped or if I confused people.
Very helpful, thank you.
So,
very helpful, thank you.
Oh, okay. Yeah, so color is color. Color is tricky.
All right, I think this is a good time to break for lunch. Thank you, Yuri.
Thank you, everyone. And I'll see you all tomorrow morning.